Conte. I am, let's see here. Yes, so good morning, or actually good afternoon, or good evening, depending on where you are. I am Joel Conte. I am the PI of the Shake Table Experimental Facility from NERI at UC San Diego. And I would like to welcome you to our NERI webinar series. Actually, this webinar is the kickoff of our webinar series. And I would like to go a little bit through some logistics. So if you have questions, please use the chat and Q&A in your Zoom window. And you can also, I believe, unmute yourself. I probably have all the question at the end. And I think we should be good to go here. All right, so I'm going to, I also want to apologize for last time, right? This presentation was supposed to be on the 13th of October. I had some last minute trouble with Ethernet in my office. So today I'm going to talk about our NERI experimental facility, which is a 6 degree of freedom shake table. But I'm going to go back a little bit through the history of the facility so that you understand it well and you understand well the new capabilities. So we have a team here, our NERI team. I'm currently the PI. There is also, you can see there are 4 co-PIs, my colleagues here. We have a site operation manager, Kurosh Lotfizadeh, who is online right now, who will help with the question and maybe even help me answer some question. And then we have development engineers. We have a financial manager helping us with managing the finance. We have 2 PhD students here who helped us a lot during the upgrade. We have an IT manager, development technician, and some colleague from the civil structures group who are we call this capacity building partners. And also with our latest recruit, Professor Alessandro Palermo. A few more things here. The one highlighted in yellow are the one who participated in the upgrade of the facility. And some of us have been involved with this facility from the very beginning. Professor Restrepo, Lely van den Einde, myself, and Alex Sherman, Robert Beckley. So the outline is I will introduce you to the Engelkerk Structural Engineering Center, then we'll focus on the shake table, and then look at some past shake table test, look at the upgrade to 6 degree of freedom based on what was the upgrade made and the performance now of the 6 degree of freedom shake table, and conclude with some new research opportunities made possible by the LHPOST6. So when we arrive at the Engelkerk Structural Engineering Center, this is the bird's eye view. You see the yellow part is the platen, the shake table platen. This picture was taken a number of years ago before the upgrade. We were testing some electrical pole with transmission line. We have also there a soil structure interaction facility with 2 soil pits, natural soil pits that can be emptied and filled with whatever soil layers the researcher wants. And we have a large reaction mass to perform some quasi-static test. You also see the building here is the hydraulic power system building. That's where all the hydraulic power is located. We also have a blast and impact facility that is also making use of some of the hydraulic power here. The facility is accredited through IAS, which means that in over 80 countries around the world, the shake table results produced at our Engelkerk Structural Engineering Center are accepted with no question asked. So now let's focus on the shake table facility. This is just to give you a history, so you understand we started in 2001. So we wrote the proposal 2001 to 2002. the facility was built from 2002 to 2004 as part of the NEES program at NSF, Network for Earthquake Engineering Simulation, with some additional funding from the Department of Defense. And then it was operated as a shared use facility under the NSF NEES program from 2004 to 2014. Then NEES became NHERI, Natural Hazard Engineering Research Infrastructure program of NSF. And we had to recompete at that time, but we were selected again and were supported from 2016 to 2022 to operate and maintain the table in support of research group from anywhere in the United States. And then there was an opportunity that came up in 2018 to write a proposal for the upgrade. And we got it in October 1st, 2018, and it took 1 year to design the upgrade and 2.5 years to build the upgrade. And then we are now under the last phase of NHERI for operations from 2022 to 2025. So the objective of the NHERI, of our shake table facility, so the vision of our site is rooted in what we think are 4 critical needs for advancing the science, technology, and practice in earthquake engineering. We need to understand much better the system-level behavior of civil infrastructure system, from the initiation of damage to the onset of collapse, including soil structure interaction, contribution of lateral and gravity load resisting system, and non-structural systems. We need very, very much data, high quality data, to guide the development, the improvement, the calibration and validation of the computational model that will be used increasingly and will allow us to progressively shift our current reliance on physical testing to more towards model-based simulation for design and assessment of civil infrastructure system. We need more data and fragility information for the full realization of performance-based design. And finally, large shake table tests, they in a way represent the ultimate validation test for new system, new components, new material, new construction methods to protect civil infrastructures against earthquakes. Now, this is a slide that we had for a long time, since the beginning. You can see a 3D rendering of the reaction mass, the platen, and you see the size of the platen, 12.2 meters by 7.6, 40 feet by 25 feet. You can see what is very important here, what is written in red, is that we had designed this facility to be a 6-degree of freedom shake table, but built it as a 1 degree of freedom system to meet the budget available at the time. You can see the peak displacement plus or minus 75 centimeters. The peak velocity was a major design criteria, which dictated, many key parameters of the facility. So 1.8 meter per second to be able to reproduce near field ground motion and the large velocity pulse. And you can see that the frequency range is 0 to 33 hertz. We have a maximum horizontal force of 680 ton. Payload, a maximum payload capacity of 2,000 ton. That's the largest in the world. And then a very large overturning moment capacity of 5,000 ton meter. So when we designed this facility, the goal was to be able to reproduce very large earthquake ground motion, especially those produced by near source earthquakes. And since we have a mild climate in Southern California, to build the shake table outside became a possibility, which remove any constraint in terms of height. We can bring any crane we want to help with the construction of any specimen. And the facility was commissioned on October 1st, 2004. And from 2004 to 2019, we conducted 34 major research and commercial projects. Most of them are research projects involving the type of structures that you can see here, building structures of different materials, wind turbine, geostructures, structures from utilities companies. So here, let's go a little bit through the facility itself. You can see the reaction mass. It's very large, 33 meter wide, 19.6 meter wide by 33 meter long, 8 meter tall. And you can see initially, so we had 2 longitudinal actuators. One of them is here. We had at the beginning the vertical pressure balance bearing, 6 of them with some big spacer block. And in 2009, we already upgraded this with vertical actuators, but they were not ported with large servo valves. So they could be used only quasi-statically, so to speak, just to lift up the platen before moving it horizontally. You can also see these tubes here. We call them hold-down strut. They are tube with a piston in the middle, a rod towards the bottom, and nitrogen at 2000 psi in the bottom chamber, which produce a downward force on the platen. So it's pre-stressing the platen against the vertical actuators to create the overturning moment capacity. You can see here the platen, one of the longitudinal actuators equipped with 2 servo valve, very, very high speed, high performance servo valve, 2,500 gallon per minute. That's what was needed to reproduce this 1.8 meter per second for peak velocity of earthquakes. They are single-ended actuators, sorry. They can push more than they can pull, but because of the symmetric arrangement, we have the same pull and push. You can see the pink plates underneath there. They're called the slider plate or the glider plates. That's what makes the platen glide on top of this top plate, the pressure balance bearing of the vertical actuators. So there is an oil film here at high pressure that takes most of the vertical load. So we have a very low friction, less than 0.5%. And this is one of the servo valve here, a gigantic servo valve. It's a four-stage servo valve because of the size of the flow, 2,500 gallon per minute. You can see the 4th stage, the spool here that moves in the sleeves. To give you an idea, the weight of that spool is 320 kilograms, 700 pounds. And you can see that the high pressure fluid would arrive in this cavity here. And then when the spool moves to the right, the high pressure fluid would go through this port, would go to the left of the piston in the actuator, and the piston would extend, and the actuator arm would extend, and vice versa if the spool were to move to the left. So this is a schema that gives you the hydraulic power system for the 1 degree of freedom LHPOST, so that you understand well. So we had only 2 pumps and an accumulator bank with a capacity of 2,500 gallon. So it's filled with nitrogen at 3,000 psi with a piston at the bottom. And then we use one of the pump to pressurize, to bring some oil below the piston and push some oil in each of the bottle until we reach 5,000 psi. At that, which occupies about the 20-25% bottom of each of the bottle here. And then when we play an earthquake, we release that high pressure oil through two valves here, blow down valves in the red pipes, and we go to each of the 2 longitudinal actuators. See this pipe here, 12-inch diameter steel pipe becomes 8-inch in the reaction mass. And then the depressurized oil, after passing through the actuator, come back through the blue pipe in the surge tank, a 20,000 liter or 20 cubic meter surge tank. The second pump is used to provide the pilot flow, the flow required to move the spool in the servo valve, and at that time to also move quasi-statically the vertical actuators. That's about it here. Now you can see here, it was from 2004, and we were testing the 1.8 meter per second. So you could see here the platen, and from underneath here, you see one of the hold-down strut here. Now, a few words about the reaction mass. The reaction mass design is very unique in many respects. It is very lightweight. It weighs 4,380 tons, which is barely more than twice the maximum payload capacity. Usually, for large shaking table, MTS would recommend 20 times, 30 times the maximum payload capacity. But here we have a very, very stiff soil. And with one of our colleagues, Professor Enrique Luco, expert in soil structure interaction with the shape of the reaction mass, he increased the radiation damping. So there is a very high effective damping of this reaction mass between 32 and 42%. And again, very stiff soil conditions, so that here we did some forced frequency vibration of the reaction block at the time. And this is some of the results. These are frequency response function when we excite the block in the east-west direction, in the longitudinal direction. And if we look at the blue curves, this is at the top of the reaction mass. So you can see, and this is all normalized for a maximum force of 680 ton, 6.8 meganewton. So you can see that there is some characteristic frequency somewhere between 10 and 12 hertz. Usually for large shake table, they like to have this below 1 hertz. That's why they require such a large mass. But here you can see that the dynamic amplification is very limited because of the very high radiation damping. And you can see also the displacement of the reaction mass is 1/4 of a millimeter when you subject it to the maximum force of 680 ton. And this is because when the block is moving translationally, it's also rotating at the same time. So the vertical displacement at the edge of the reaction mass due to the rotation is 0.15 millimeters. And so recently we did much more tests for the other directions now, and we are still cleaning up the result, but there was no surprise. It's all consistent with this. So a few words now about the controller. The controller, so this is a block diagram of the controller. The user would provide, for example, a ground acceleration record called reference, the reference signal. And then the reference generator of the MTS 469D controller would integrate it once and twice to get the velocity, displacement, differentiate it once to get the jerk. And these 4 signals are used in a feed-forward way in the control loop. So there is a feed-forward gain, 4 of them here, that are used to shape the transfer function of the shake table in different frequency range. And then in terms of the signal feedback, there are displacement feedback from each of the actuators, vertical and horizontal. There is acceleration feedback from the accelerometers installed on the platen. And the pressure transducer or force sensor feedback, right? So then the feedback generator part of the controller is using some composite filtering to estimate to produce the best estimate of the true feedback displacement, feedback velocity, feedback acceleration of the platen. And then the control loop is closed on the displacement. The target displacement is compared to the feedback displacement that we often call the achieved displacement of the table, and the error is computed and is multiplied by a displacement feedback gain. Right? So here, only this displacement feedback gain is non-zero. These one are kept zero for concern about stability and difficulty in tuning the control. And then the other feedback gain that is not zero is the delta pressure feedback gain. That is very important. We'll discuss it a little bit later. Right? And then all the control algorithm results into a command signal that is sent to each of the servo valve of the system. So when we tune the table for an earthquake record that will be played for a specimen that will be constructed in the future, there are basically 3 steps. The first step is to adjust the feed forward and feedback gain that I just described to you manually, right, in a certain sequence until the transfer function of the table gets, as close to 1 as possible. For example, you see that black curve here. Right? Of course, it cannot be brought exactly at 1 because it's a dynamic system. It's a complex dynamic system. And then and this is done using a white noise, moving the table with a white noise acceleration signal, long duration, multiple minutes, and so on. Then when this is done, the transfer function of the shake table is estimated as accurately as possible, because then it is used in these iterative time history matching techniques that consist of iteratively modify the drive file so that what comes out on the table is as close as possible to the reference signal, to the desired signal, right? Because now we know the transfer function of the system, so we can, in a way, modify the target ground motion by 1 over the transfer function. In simple terms, it's more complicated than this. And then you can see that iteratively, we reduce the discrepancy between what comes out on the table and what we want to play on the table. Here, for example, the drive file at iteration 7 would be used when later on the specimen would be placed on the table. And when we had a 1 degree of freedom system, we were able to, usually we did not have to touch anymore the tuning of the controller after the construction of the specimen on the table. We were still very good, except for a few exceptions. But now the situation has changed. Where 6 degree of freedom shake table, the presence of the specimen is changing quite a bit, the dynamic of the specimen table system. We have to relearn the transfer function of the table and the specimen and do some modification of the drive file that we obtain under bare table condition. I'll talk more about this at the end. So here we've always been proud about the accuracy of our shake table in reproducing earthquake ground motion. You see an example here from the 1994 Northridge earthquake. That was, the target is in red and what is achieved by the table is in blue. You can see a zoom here and you see the pseudo acceleration spectrum of the target motion and the achieved motion, and the and the spectral displacement here. It's very difficult with a very large shake table to have this degree of accuracy in reproducing signals. We have also a large inventory of sensors. We have 13 nodes of 64 channels, so over 800 channel of sensors, 24-bit AD resolution, simultaneous sampling. We also have many sensors, as you can see here, accelerometers, displacement transducers, string potentiometers, inclinometers, load cell, soil pressure transducers. We are just installing now the next generation of GPS, which is GNSS, making use of multiple satellite, and we can measure the displacement at 100 Hertz. We're still looking at which accuracy. We were hoping to achieve 1 or 2 millimeter accuracy, but we are still checking and validating the system. We have many high-speed cameras. As you can see here, we have a fully configured end-to-end live video streaming production system, and we are on social media, YouTube, Facebook, Twitter. We have also some calibration equipment, which is required in order to have our accreditation. We need to regularly calibrate the data acquisition system and the sensors. So now let's look at some past shake table tests using the 1 degree of freedom version of the table. You can see pictures of a number of specimens that were tested here. You can see the first one was a slice of a 7-story building. You see a bridge pier here, full scale. You see a metal building, a wind turbine, the laminar soil box with a sound wall embedded in some soil that is in the box. You can see a soil retaining wall here, making use of our large soil box that I'll show in a few minutes. You can see here a 4-story wood frame with a soft story, such as the building in San Francisco, and so on and so forth. So now let's focus on one of them. You know, this test that was a 5-story, full-scale 5-story reinforced concrete building with non-structural component and system. First tested on base isolation by having a base isolators at each corner of the building here. And then later on tested on fixed base. So this, you know, had 2 different type of facade at the bottom and then the top. Heavy precast concrete at the top, light facade at the bottom. And there were different floor occupation. You can see that we also inflicted some fire after an earthquake to simulate fire after earthquake, actually here, and then to place some earthquake after the fire to simulate the effect, aftershocks, the effect of aftershocks after fire. And you can see here that we have an intensive care units and then a surgery suite at the top. We had a fully working elevator here. We had stairs. And here you're going to see an animation, some movies. So you will see the time history of the ground acceleration, which is the table acceleration, right here. And then you will see the shear strain through the base isolators. You can see the displacement on the 3rd floor and on the 6th floor. And here you will see the total shear at the base versus the shear strain in the isolator. And then the interstory drift ratio along the height of the building, the floor acceleration along the height of the building, the story shear and the story moment as a function of the height of the building. And this is the finite element model of the specimen. So let's play, and you will see also a comparison of base isolated and non-base and fixed base for the Peruvian Ica earthquake of 2007. So the same earthquake actually scaled higher up for the base isolated at 140%. And so you will see that. So let me push the button here. So there was a maximum shear strain of about 140% in the base isolators. You can see that we can reproduce, and now you see this comparison, base isolated on the left and fixed base on the right, on the top story with the intensive care unit. It's very, very good publicity for base isolation. You can see that it's easy to reproduce the experimental result because the building is quasi-linear. All the deformation and nonlinearity are concentrated in the base isolators. Now you can see the same building, but with fixed base. So we are here at the 3rd story, and you can see below that a column on the 2nd story with the beam. So you will see some damage mechanism. You will see here a fracture of the rebars at the bottom of the beam that go through the column. They fracture at the face of the column, and you will see here the initiation of a shear punching failure mechanism. So these things are still very challenging to predict analytically with numerical models, to predict accurately and reliably, especially like if in blind prediction, right, where you cannot have access to the data and massage your model based on the data. You can see here the large crack that opened. This happened at 8 locations in the building simultaneously. So here you can see the 2 large soil boxes that we have. We have a laminar soil shear box and a stiff soil confinement box that can be attached to the platen to study soil foundation structure interaction, and to also investigate soil liquefaction and its effect on the seismic response of structures in terms of soil lateral spreading, for example. We would put a bladder in the box before putting the soil layers and then saturate the soil. So here is also a test where that the large laminar soil box, you can see it emptied here. You can see the placement of a pile, a single pile. And then this is after the various soil layers have been installed. The laminar soil box was installed on a ramp to simulate a sloping ground. The effect of lateral soil spreading are accentuated when there is a sloping ground. And you can see the movie here. I'm going to play the movie. So the soil, the most vulnerable, the soil layer most vulnerable to liquefaction was in this region here, where you have the largest shear strain. You can see a little water leak here at the bottom, and you could see, right, the pile progressively migrating through the soil, and the soil lateral spreading phenomena around the pile here. So then let's talk about the 6-degree of freedom upgrade of the table. So we had looked for funding to do this upgrade almost from the beginning, almost from 2004. We didn't succeed until 2018 when there was an opportunity to submit a proposal for large facilities at NSF, and we were funded on October 1, 2018. We took 1 year to design the upgrade in collaboration with MTS Systems Corporation. I forgot to mention them also for the creation of the initial facility. It was basically a collaboration between a group in our department and MTS System Corporation. And the upgrade took 2.5 years in the midst of the pandemic. We had planned 1.5 years. It was technically very complex. So these are the ground motion that we considered to design the upgrade. We wanted to be able to reproduce triaxial ground motion from Tabas 1978 earthquake, Chi-Chi, Taiwan, Kobe, Northridge, Nepal, at Kathmandu, and then an artificial earthquake ground motion that is used for seismic qualification. Just to show you each of these 6 records, what they require in terms of peak flow rate. They require, you see the maximum of all is the artificial ground motion, 28,000 gallons per minute. And then in terms of total flow, 2,200 gallons. Right? And the accumulated bank, this should represent only about 20%, 25% of the accumulated bank. So that's why we chose an accumulated bank of 10,000 gallons. So we had to multiply our accumulated bank by a factor 2. So now 10,000 gallons. And now we have 6 blowdown valves instead of 2, and we bought 2 more pumps. So we pressurized the accumulated bank with 3 pumps. One of them is to provide the pilot flow of all the servo valve of all the actuators. And when we reproduce a ground motion, again, we blow down the accumulator bank, and we have the direct pumping from 3 of the pump, but it's a couple of percent compared to what comes from the accumulator bank. We did a calculation once when we reproduce a large ground motion. If we take the energy to reproduce a large ground motion divided by 30 seconds, let's say the duration of the ground motion, we get an average power that is similar to the peak power requirement of a small city of a few thousand people. So here we have now a full ring on the inside of the reaction mass in red for the pressure. You see now we had to double the number of lines. We can have a peak flow of 40 feet per second when we reproduce an earthquake in these pipes. And then we have a return ring, you know, the blue one. So this is a picture of the accumulator bank, very tall. We have 75 bottles of 135 gallons each. Again, fill of nitrogen at 3,000 PSI. And then we pressurize the oil underneath, under the piston, the bottom 20 or 25%. See, each bottle is equipped with the pressure transducers. We monitor the pressure continuously. This gives you, we bought 2 more horizontal actuators and assembled them in V-shape. So now these 4 V-shape actuators allow you to do east-west motion, north-south motion, and the yaw of the platen. And we already had prepared everything. The holes in the reaction mass were already there to receive the post-tensioning rods, to post-tension the base plate here of the swivel base of each of the actuator. You can see also the 4 pedestal in brown color here that support the platen when we are not using the shake table. And then you can see the 6 vertical actuators with now equipped each of them with a very large servo valve. This is the one of the vertical actuator with the servo valve. It's a 5,000 gallon per minute. So same peak flow as the horizontal actuator who have 2 servo valve with 2,500 gallon. This is, I think, the largest servo valve that MTS has ever built. You can see here we also added 1 hold down strut to maintain, our high overturning moment capacity. A few words about the north-south direction of the platen. So when we have the V-shape actuator, they have the kinematic capability to move the platen 43 inches in the north-south direction. You see that we have 50 inches here, but we would unseat the platen already after 17 inches. And we would have an impact between the belly of the platen here and the reaction mass with 34 inches here. So we need to we have 3 lines of defense to protect against this, right? This could happen during a loss of electrical power or a programming error of the operator of the shake table, right? So then we have three line of defense. The first one, we have interlock in the motion controller of the shake table to detect some travel overrun. And then if they are detected, the test is aborted in a soft manner as possible. And then we have a second control loop with auxiliary sensors that we call limit switches in case the first one is not detected. And if both of these are not able to detect the travel overrun, then we absorb the impact using some bumpers that were designed, crash protection devices that you can see here. We have 2 on each side. You can see each of them, how they look like. So the design criteria was to stop a specimen of 1,000 ton moving at 1 meter per second, to stop it with a displacement of the piston here of 2 inches. You see, we have 42 stainless steel rod that would yield and absorb that energy. So remember, we have 17 inches here, and we want 2 inches to absorb the shock. So 17 minus 2 is 15 inches. So that's why we limit our north-south displacement to plus or minus 15 inches of 38 centimeters, plus or minus 38 centimeters. Now the platen, imagine this rigid platen, rigid box, 6 degrees of freedom in a three-dimensional space, right? We have the platen, so it has 3 rigid body degrees of freedom. And each actuator, when the oil is pressurized, represent like a spring. Right? The oil column in each actuator, horizontal and vertical, is like a spring. So if you do a 6 degree of freedom eigenvalue analysis, you would get the predicted oil column frequency that are here. As long as we take an effective oil bulk modulus of 60% of the actual oil bulk modulus of the hydraulic fluid to account for entrained air and other source of compliance. This is by experience that we have this knowledge here, right? And then these are the identified oil column frequencies. So you can see that the first one, the platen is moving in the north-south direction as a rigid box at 9.22 hertz. And then the yaw is the second one at 11 hertz. And then in the longitudinal direction with the pitch with the rotation at 11.95 hertz. And then we have in the vertical direction at 40 hertz. All these, if you don't do anything about this, you're in big trouble. They pollute the signal, the fidelity in signal reproduction of the target signals. Right? They would pollute tremendously. So the delta pressure feedback of the controller is damping these oil column peak beautifully, right? Completely not completely, but almost entirely, right? So that's how it works. And now a few more words about the controller for the 6 degree of freedom shaking table. So for every degree of freedom of the 6 degree of freedom now, it's exactly the same block diagram as I showed you for the 1 degree of freedom. So now how are, for example, the dynamic cross coupling between the degrees of freedom, it would be taken care of now by the inverse of the transfer function. Now the transfer function is a transfer function matrix, right? 6 by 6. It has off diagonal term and diagonal term. Right? So we are making use of all of those to minimize the cross coupling between degrees of freedom. And then the controller, of course, is making use of a lot of transformation between the Cartesian degrees of freedom and the actuator degrees of freedom, and so on and so forth. So now the performance of the shake table. You can see here the axis, right? X is east-west, X, Y is north-south, Z is vertical. So this is the performance characteristic of the LHPOST6. Still from 0 to 33 hertz, still a maximum payload capacity of 2,000 tons. The one in Japan at the defense is 1,200 tons. We are now the largest payload capacity 6 degree of freedom shake table in the world. Now the displacement here, you can see plus or minus 89 centimeters. We were plus or minus 75, right? So we gained. And then plus or minus 38 centimeter in the south, plus or minus 13 centimeter in the Z direction. And the peak velocity, we were at 1.8. We are now at 3 meters per second in the east-west, 2 meters per second north-south, and 0.45 meters per second vertical. At the E-defense, they have 2 meters per second in both here. And you can see also that the maximum force, horizontal force, we could go to 10.6 meganewton east-west and 8.4 meganewton north-south. We are not allowing this at this point in time, because initially we had designed the reaction mass for 6.8 meganewton longitudinally and transversely 3.4, half the capacity. But there is most likely quite a bit of overstrength. We need to do a much more detailed study to see how much of this 10.6 and 8.3 we can safely use. We will do this in the future, but right now we are capping it up at these maximum forces here. And then you can see the peak rotation in the pitch, sorry, in the roll, the pitch, the yaw. And we have two columns here. I'm sorry, I didn't say it. This is bare table condition, and this is a maximum payload, rigid payload of 500 tons, centered on the platen. It's almost the same. It's just the velocity here that changes. It actually increases when we have a payload compared to that. So these rotations seem small. Large rotational ground motion for near field large earthquakes have never been measured. They will hopefully be measured soon in the future, but they've been predicted through elastodynamics and so on. And these are large rotation. And you will see a movie when you have plus or minus 1 degree, it's visually significant. So now you can see that the target, this is basically to show the fidelity in signal reproduction for one of the earthquake from Takatori record in Kobe earthquakes during the acceptance test. You can see the acceleration in the X, Y, Z direction, then the velocity X, Y, Z, and the displacement X, Y, Z, and the tripartite spectrum. And you can see in red is the target, what you want, the real earthquake record, and in blue, what is achieved by the shake table, with the relative root mean square error in percent indicating each time. So this was for bare table condition. We are still very accurate for 6 degrees of freedom, as you can see. Now you can see here 94%. The Tabas earthquake with 3 components, 3 translational components. So this was during the acceptance test. And now this is a 6 component ground motion record, but it's a synthetic ground motion record. It has 3 translation and 3 rotation, and the rotation do not exceed plus or minus 1 degree. So even though, look at the, it's pretty large visually. And now this was the first demonstration test that we performed after the upgrade. We tested our shared use modular test bed that was funded by NSF as a supplement for our NERI site. You see, it's a 3-story steel structure, very modular, that researchers can make use of. It has shear fuses. You know, you can test different type of braces. You could insert a shear wall inside the frame to test the dual system and so on. So here you will see a test under Northridge earthquake, 3 translation for two different configuration of the specimen. If you look at the platen, you can see it going up and down. And then I'm running out of time here. Let me speed up a little bit for the last few items. We are developing a digital twin of the shake table with a PhD student. It will allow to do pre-test simulation, dry run of shake table test way before construction of the test specimen. It will be able to be used for offline tuning or pre-tuning of the shake table controller, investigate control table specimen interaction, and use for offline training of shake table operator, development of next generation shake table controllers, or for real-time hybrid shake table testing. So this is the model accounts, includes all the horizontal actuators, the rigid platen, the vertical actuator, the hold down strut, the sliding surfaces, the various sliding surfaces, and the energy dissipation system. This model can be connected with the same shake table controller, the MTS 469 shake table controller. So it has hydraulic dynamics, it has kinematics and dynamics of the platen and the various component connected to the platen, and so on and so forth. And now the new research opportunities made possible by the LHPOST. I have a couple of slides here. So the LHPOST6 now allows us to subject large 3D full-scale or large-scale model of structural system, geotechnical or soil foundation structural system, to multi-directional shake table, multi-directional earthquake excitations, and including the effect of soil structure interaction, nonlinear soil behavior, nonlinear structural behavior, soil liquefaction, and seismic compression. Here you see from a paper of Trifunak, a nice cartoon that you see a building. If you have horizontal base excitation, you will create drift response in the building. If you have base rotational acceleration, you also have drift, and in some cases these drift they add constructively, and if you include the rotational, you could push the building over the edge. And again, now I just have about 5 pages. I'm going to go rapidly. Topics that could benefit a lot from this shake table facility as the better understanding of the inherent damping in structures. There is no consensus yet about what is the best damping model to use when we perform linear and nonlinear time history analysis. We think that targeted experiments on large-scale building specimen with or without non-structural components and bridge substructures could be very helpful for that. Experimental study of dynamic soil foundation structure interactions. We could do several things like listed here. We could do a numerical study of a soil foundation structure interaction response, and then input on the platen the total foundation motion predicted numerically, and then test the superstructure on the table and compare with the numerical simulation results for the superstructure. Or we could put the large soil boxes and subject them to a multi-directional excitation on the platen, or do some hybrid test. Seismic safety of unreinforced masonry building. We know that unreinforced masonry walls tend to behave much better when there is only a horizontal excitation and no out of plane excitation or no vertical excitation. So including these out of plane, horizontal and vertical can play an important role that needs to be investigated. Seismic performance of reinforced concrete and reinforced masonry wall structures. Same thing, the importance of bi-horizontal excitation and vertical ground excitation plays an important role and needs to be studied and the results used to improve the current design provisions. Structural concrete and precast concrete system. There is a push now, as you all know, towards innovative seismic resilient, low damage, called concrete systems. They need to be tested carefully under multi-axial seismic excitation and validated under more realistic condition to improve and validate the modeling and the analysis capabilities of this system. Use of high strength material, steel and concrete, or advanced material like fiber reinforced concrete. Commercial tilt-up buildings, they did not behave well during the 1994 Northridge earthquake, still need to be better understood. Structural steel system, there is also a push for innovative low damage, seismic resistant systems. Non-structural component and system, there is a need to develop a unified, reliable, unified seismic design methodology accounting for multi-directional earthquake excitation. Advanced or innovative earthquake protective system like passive system or even semi-active system often have been tested at small scale, but test at large scale would accelerate the acceptance, in the real world structural engineering community. And these systems often have a complex kinematics that need to be investigated under multi-directional earthquake input excitation. Building structures, the interaction between lateral and gravity force resisting system and non-structural systems still require a lot of research for better understanding. And also the validation of seismic retrofit methods for older non-ductile, non-code compliant building structures. Before they are implemented in the real world, they could benefit a lot from being validated on large-scale shake table test. Energy power structures, infrastructure supporting the use of renewable energy sources like wind turbine farms, solar arrays, hydroelectric concrete dams, electrical substation of all sorts, and nuclear structures and system and subsystem and components. You can see here after the current test on the cross-laminated timber buildings, we will have a test for Sandia National Laboratory of a dry storage cask with the fuel assembly. surrogate fuel assembly and dummy fuel assembly inside. And finally, here is the last slide, the bridge structures. There is a need to understand better the behavior of slender columns of bridges of complex highway interchange system when subjected to bi-horizontal excitation and vertical excitation at the same time. You see here also multi-directional dynamic experimental evaluation of a bridge superstructure with the abutment and the substructure interactions. Structural health monitoring, what does it do here? All the data that is collected from the test performed on the LHPOST and the LHPOST6 are invaluable data for researchers involved in vibration-based condition assessment methodology, damage detection methodology, right? Because we usually go from no damage to a lot of damage, and we have all the data, dense data arrays. So these are unique data sets for this research community to help them resolving the remaining obstacle, preventing the reliable real-world implementation of structural health monitoring methodologies. And finally, to enable the research need for the full realization of performance-based and resilient-based design. Right? We already talked about development of fragility function and development, calibration, and validation of numerical models that are highly needed at the material level, component level, and system level for performance-based engineering. And now you see here a few pictures about the first experiment after the upgrade of the shake table. This was a 10-story cross-laminated timber with rocking wall. You see 3 pictures of the specimen. You can see that in the bottom third, they built also a non-structural component, the facade system. It's a team consisting of 5 universities. The PI is Professor Shai-Ling Pei from Colorado School of Mine. You can see here some movies that I'm going to play. So this is the Loma Prieta MC level earthquake. And you will see the shake table moving here. You will see here that's a column from the gravity frame with a bidirectional hinge at the bottom. And this is a shoe, a steel shoe surrounding the corner of the rocking wall and preventing damage on the rocking wall. Stop it here. And so you could definitely see the second mode and even the third mode of the building. And the wall would uplift here about an inch or slightly above an inch for the largest earthquake. And it was subjected to 100 earthquakes, among which many at the MCE level and pretty much no structural damage. This will be the subject of the next webinar. I will not say more. And now here, the last slide is to show you for one of the ground motion, not the one I showed you, another one, Northridge 1994. You can see the reference earthquake record in the X, Y, and Z direction in red, and the feedback, the one achieved by the table. You can see the relative root mean square errors now, 35%, 28%, 44. They are not in the 10 or 50 or 10, 15% that we have for the empty table, right? So it's much more challenging now when we have a specimen, but still very good overall. And there is room for improvement of the tuning process that we are using, and also improved, the algorithm of the controller of MTS 469D. So thank you very much for your attention. You may have some question, and sorry I went a little bit over time-wise. There is some information here that you may be interested in, some papers describing what I went through. And if you want to contact people at the site, I would, the most responsive person will be Kurosh Lotfizadeh, but you have all the other PI and co-PIs. So you can unmute yourself, or let me see, Kurosh, maybe you can help me if some question were already typed.
Of course. Yeah, there's currently no questions in the chat or the Q&A. You're more than welcome to use those two features in Zoom, or just unmute yourself if you'd prefer to speak your question.
Can I ask a question? Can you hear me?
Yes,
of course, of course.
Hey guys, nice. A quick question. So on your shake table on the rotational part, you can put a small soil box, let's say a foot or half a meter of soil, and then put the structure on top of that. Is that possible?
Yes, we can do this. Something I didn't mention is that, you know, the laminar soil box, you have this frame that can move relative to one another only in one direction. It was made for a 1 degree of freedom shake table. Now we need to most likely build a new laminar soil box that can.
But what I'm saying is I don't really, I mean, I know what the propagation of waves through the soil is. I'm really interested in that half a meter zone beneath foundation. That's where most of the action happens. And even if it's a rigid box, but I just need foundations to be sitting on half a meter of soil and then have some structure on top. So I want to measure, I can analytically calculate the dissipation of energy in soil, in the interface, and in the structure. I want to validate that. So can you put a rigid box, whatever, half a meter wall with some soil and then structure on top of that?
Yes, we can.
Okay.
Yeah.
Okay. Good. Thank you.
Okay, we have a question in the Q&A. The question is, regarding the damping, what percentage of damping do you assume in a 6 degree of freedom shake table while developing algorithm?
I see. So maybe, I think it's Rajendra. If you can unmute yourself, Rajendra, and maybe be a little bit more explicit.
Yeah, initially you presented you assume more than 30% damping in 1 degree of freedom shake table, right?
Yeah, this is the effective damping, you know, of the reaction mass of the table embedded in the soil. So
Okay.
it's not something that, I mean, it's a property of our facility.
Yeah.
To justify why it's okay for us to have a light reaction mass, right? But it's not something we are using when we do some test. So that's why I was not sure.
Okay.
When you say while developing algorithm, maybe you can specify.
I think you are producing the synthesized ground motion, right? And then you are matching the ground motion with the numerical simulation. Then how you cope with those parameters?
I see. Maybe what you mean is, you know, when we were designing the facility, we had one concern that when you control the shake table, you want to control the absolute acceleration of the table and therefore the absolute displacement, right? But the actuator, they are between the reaction mass and the table. So they measure the relative displacement between the table and the reaction mass. So if there was a lot of displacement between the reaction mass and an inertial reference frame that does not move, then we could have been in trouble, right?
Okay.
But you have seen from what I showed you, even if you apply the maximum force on the reaction mass, you have 1/4 of a millimeter of displacement of the reaction mass. So this is not creating a problem for the control of the shake table.
Okay.
To use the relative displacement between the reaction mass and the platen and the absolute acceleration from the accelerometers. for controlling the table.
Okay, thank you so much. This would be nice experimental verification for all the structure, right? Thank you so much.
Yeah, you're welcome.
Yeah.
As you think about more questions, let me also put here the next webinar on November 15 will be by the PI of the 10-story building. Right now, we have removed the 4 top stories of the 10-story. So it's a 6-story that will be reconfigured in 2 or 3 different ways. And there is a new research team with the PI is Professor Andre Barbosa from Oregon State University. So now Professor Shailing Pei and his team, they are studying, analyzing the huge amount of data that they collected with the 10-story building. And he will be the presenter of the next webinar on November 15 at the same time. So let's see if you have more questions. Again, feel free to unmute yourself. We can also, if you email us, you know, at the different email that I have put here. And if you want to suggest speakers for our NERI webinar series, we plan to have 1 speaker per quarter. We would, of course, consider your ideas about. It doesn't have to be somebody who tested here at UCSD, but it could be speakers about very important research questions in earthquake engineering, grand challenge in earthquake engineering. So feel free to communicate your wishes to us. So no more questions from anybody.
All right. Well, there's no more questions in the Q&A. Please feel free to reach out to us via email if you have any questions in the future.
Yeah, again,
I have a question. Sorry, will we be able to get some of those slides? I mean, the last one, I don't want to take a screenshot of the emails. Can we get the slides? Is there a chance, or just send us these emails, this last slide?
Yeah, sure. We can create a PDF version of the slide.
Yeah, thank you.
And if those of you who want them, please email Kurosh. Very good. So thank you very much for attending our first webinar from this new webinar series, and wish you a good end of Friday, a good weekend, and please come to the next one by Professor Shailing Pei. Thank you very much. Goodbye, everyone.
Thank you very much, Professor.